now let's go on to spherical coordinate systems. This one is definitely a bit different than you would have seen. So I will do my best to describe this without, being there, using my meter sticks and vectors in class. So let's first describe how to indicate a point in space. So if you have a point in space from the origin, then you can talk about any of these points. So any point in space from the origin is basically on a sphere. So you could draw like a sphere or something. So then you can talk about the radius of that sphere. So at some point, there's a distance from the origin to that point. So we call that distance rho. So it's like r. All right, so that's the kind of the Greek letter r. So we call that rho is the distance from the origin. Then we describe, so for this point, we want to have, there's an angle you can describe from the x-axis out to wherever the point is. Okay, so from here, it's the x-axis out. So that's the same theta as in polar. So we'll call that rho, and then theta is the angle from the x-axis out. So that would describe all of these points. It's basically like a circle right there, right? All right, so then, so there's a bunch of points right in here that are that radius and that angle from the x-axis. So from there, we want the next angle is phi. So phi is the angle from the positive x-axis to the point. And so phi can go all the way down to here, and usually you just say 0, and so this is the direction you're going all the way to pi halves, or I'm sorry, pi, all the way to pi. Usually you don't go around like that. You just move this angle around to over here. So theta is the angle from the polar axis to the xy, in the xy plane. So that's just like polar coordinates. And then phi is usually the more difficult one to visualize. Phi is the angle from the positive z-axis to wherever the point is. And then you have some domain values for your angles in rho. So rho is, of course, positive. If rho is 0, then, of course, you get the origin. Your theta is, like in polar, 0 and then all the way around. So it's 0 to 2 pi. And phi, we usually just say it's 0 down to pi. So it goes from here down. I do recommend on this one, if it's not clear, to look at a three-dimensional case like in your house, pull up some more videos. I just tried to find one, but they ended up switching the angles on me, and so it didn't work. I was going to try to embed it in here, and then I just gave up. There's just too much stuff out there. That's one of the reasons I'm doing all these videos, because I want you to see how it's done in our book and how I'm describing it. All right, so, and I'm not going to go through all these derivations. Please look at it in the book if you have some time to derive these change of variables. But basically, the distance formula, 0 to the point, is this. So rho squared is r squared plus y squared plus z squared, which indicates basically it's like a sphere all the way around. And then using trig, you can solve for your x, y, and z, and you get these different values. Obviously, you'll be able to look those up on your exam. It'll be open book, open note. So here's a couple examples we want to go through. If rho is fixed, then you end up with a sphere. Theta and phi are arbitrary, so it goes all the way around and then all the way down. So you get a sphere. Then, what if we have that theta is fixed. So theta goes out and stops. So then what do you get? Rho is anything, and phi goes from 0 to pi. It goes down like that. So if that's fixed, you get all of these values and then all of these values all the way down. So you get basically a plane, but it stops right here. So it's a plane that goes out like that. So you can see a plane from the z-axis. And then the next case we would like to describe is if phi is fixed. So phi comes down and stops, right, like that. And then rho can be anything, and theta can be anything. So then what you get is a cone. So spend a little time thinking through that, pausing it, looking at the book and stuff, and then picking some values. The first few homework questions are about fixed values for rho, theta, phi. All right, so then our function, when you do your integration, looks like this. So we end up getting the triple integral. So triple integral over the solid Q. So then you get f of rho theta phi dv is equal to, and then this is your triple integral with your limits. And so you're going to get this extra integration factor like before for polar, but it's not just r, so you'll see. So you have rho goes from a to b, which of course may be functions of phi and theta later. Then the order doesn't matter as much, but usually we go theta next. So theta goes from alpha to beta, just like polar. And then phi, we'll say, goes from C to D. Then you have your function, f of rho theta phi. And then you're integrating a factor that goes in there. You end up getting rho, you got to throw in there, rho squared sine phi. Oops, I wrote that wrong. Rho squared sine phi. Like that. And then it's d rho, d theta, d phi. So d rho, d theta, d phi is usually the order we do that. So let's look at this example, just converting. Okay, so let's take a look at this. So evaluate the triple integral of cosine x squared plus y squared plus z squared. And I was going to not do that yet. Raised to the 3/2 dv, where the solid q is this. So what's this solid then? Okay, yeah, that's a sphere. It's written right there. It's a sphere of radius 1. So that's your solid you're going to integrate over. So again, we can substitute directly for what x squared y squared z squared is. So we go back here. X squared y squared z squared is your rho squared. Okay, so let's convert that. Right, so this is going to be your rho squared right there. And then you integrate around the sphere. So we'll talk about what that is. So let's set up our integral. So we want to, I think that might have been the directions, to convert to spherical. Okay, so let's convert this to spherical. And we have our triple integral, like that. And then it's going to be cosine of, and then that'll be rho squared raised to the 3/2. So now you have to place in your rho squared sine phi. You have to do that next. That's like that little r factor. Again, I didn't go through the derivation of that. There's a real, well, little easier way to show that in our next section with Jacobians, which we'll see later, and how that pops out essentially. All right, so I'll change the color of that too. Let's do, so you place in your rho squared sine phi, and then the order is around the sphere. So you have a sphere. So I like to draw a little sphere over here, draw in your region. This one we kind of already know, but that's going to be your habit, right? To draw in your sphere. So you have your sphere, or your region, I'm trying to say here. So your rho goes from 0 out to the surface,